Anytime that we build robots to do work outside, the challenges mount. Roads and off-road mobility are more challenging than factories. But the challenges are redoubled for aerial robots. The physical demands of flying impact every system on the robot. Sensors and actuators have to support full mobility in 3 dimensions, and energy requirements are high while weight has to be kept low as possible. The entire control loop has to function much faster. And yet, the challenges of aerial mobility are what made aviation an early and consistent adopter of robotic technologies. That's right, piloted aircraft are robots, even when the pilots are on board. Piloted aircraft often include robotic assist technologies that operate the aircraft autonomously when they're turned on by the pilot. The best example is the autopilot found on commercial aircraft, and that was actually invented by the Sperry Corporation shortly before World War I. While we don't normally think of a plane flown by an autopilot as an autonomous robot, it is, at least when the pilots aren't at the controls. An autopilot is an embedded robotic system with autonomous self-control using sensors to guide movements. And even better, all the self-control technology assisting human pilots is equally available for unmanned aerial vehicles too. And unlike aircraft that carry human pilots, unmanned aerial robots can be almost any size, from vehicles as big as commercial passenger aircraft to microvehicles the size of insects. And they can even execute maneuvers too stressful for a human body, opening up new design and new performance possibilities. Aerial robots go up by a whole host of names: drones, unmanned aircraft, unmanned aerial vehicles, unpiloted aircraft, unpiloted aerial vehicle, unpiloted air system, and remotely piloted aircraft. Unmanned drones come in 2 types: fully autonomous and remotely controlled. And autopilots operate unmanned aircraft like many commercially available drones. The drone you see in this clip is a Walkera Tally H500, and it's a hexacopter. It has 6 propellers that provide the thrust for lift, keep it aloft, and thrust for moving forward and maneuvering. You control the Tally hexacopter using a radio control console that transmits and receives signals, including video, from the drone. Now, what's really cool about what you see in this video clip is that the drone is controlling itself to remain stable. One of the great illusions in robotics is when an inherently unstable robot, like a hovering hexacopter, isn't moving. It looks like nothing is happening. And that's the illusion. To keep the robot still takes all sorts of control that you can't see in action until we perturb the system. If you were to walk up with a stick and poke the drone, that would be a perturbation. Now, real-life perturbations come in the form of wind, or if the drone is near trees, brushing against branches. Here's something else you need to know about just hovering. Drones can use active ping sensors located on the bottom of the craft and pointed to the ground in order to measure altitude. If the distance of that ping sensor, what it measures, is not 1 meter, let's say, and it's set for 1 meter, then the thrust is adjusted to keep the craft right at the height that's desired by the controller. Now, maintaining that height is an example of negative feedback control. The actual height is constantly measured by that ping sensor and then adjusted to reduce the difference between the actual height and the desired height. The feedback is the information that you get from the sensors about the actual height. Now, when the Tally H500 is hovering, it is working on autopilot. It's doing the work of coordinating all 6 of those motors for me. And when I step into the control loop, and I do things like control altitude, heading, and speed, I can even alter the amount of work that the Tally 500 is doing for itself. Now, the moment I take over full control of a complicated flying machine is the moment that I get into trouble. Flying a hexacopter is very complicated. One of the most important features for any drone to have is landing. You want a drone to be able to autonomously land to avoid crash landing. So drones like the Tally H500 have a built-in landing autopilot function that help you preserve your investment in that robot. Because the Tele H500 has autopilot functions but also allows me to control it, it's a remote-controlled drone with some autonomous functions. Most drones are this mix of remote control by a human and autonomous control by the robot. What varies among drones is the degree to which they offer autonomous autopilot functions. For example, an old-fashioned radio-controlled airplane offers absolutely no autopilot functions, and you really have to know what you're doing with these remotely piloted aircraft. You actually have to be a pilot. They're easy to lose and easy to crash. One of the great safety features built into the Walkera Tele H500 is that if it flies out of communications contact, it will automatically return to its starting position. It uses GPS navigation to accomplish this. The Tele 500 makes flying look easy, but to understand just how much the drone is doing for us autonomously, we need to take into account the challenge of having your robot work in the air. Designing and building an aerial robot all begins with the basics of flight that we've just talked about: getting airborne, staying airborne, and landing gently. Now, the bodies of robotic aircraft need to be lightweight to minimize the energy needed to keep the drone aloft. Bodies also need to be aerodynamically shaped to help the actuators generate lift and reduce drag. If engine power is lost, it's also useful if bodies can glide, parachute, or otherwise survive an emergency landing. The Tele H500 is lightweight, weighing only about 2,000 grams or about 4.5 pounds, including its battery and camera. The retractable land legs are made of carbon fiber, which is known for its high strength-to-weight ratio. Lightweight, stiff, and resilient plastic makes up the main fuselage. You can see the drone's peculiar shape. It's very broad in one dimension and thin in another. And that broad horizontal dimension needs lots of area in order to house the propellers. The narrow vertical dimension needs to be thin in order to present as little resistance to forward flight as possible. The actuators of drones need to be lightweight as well. If actuators are actively generating lift as well as forward propulsion, like we see in helicopters or these rotary wing aircraft, then they need to have a high power-to-weight ratio. One of the ways to get a motor to be small and powerful is to trade off torque for power. You'll find a motor with high torque in a hand drill. That torque gives you the leverage to drive a screw at slow speeds. Because power is by definition the product of force and velocity, high torque motors are low power because they don't generate high velocities when driving in a screw. The drone's motors take the opposite trade-off: fast with low torque. So for the motors of a different drone, one called the Parrot AR Drone 2.0, the motors are brushless in-runners with a combined power output of 14.5 watts. In-runner motors are DC motors that spin extremely fast. They lack a magnetic iron stator core, so that makes them very lightweight and more efficient to spin. But the lack of that magnetic stator means they have virtually no torque at low speeds. Instead, they are built to operate at very high velocities, at 28,500 rotations per minute. The sensors of drones are also of two main types. Proprioceptive sensors monitor the state of the robot, and they must do so with high speeds of reaction and good accuracy. So when we look at the sensors of the Parrot AR drone, we see that it's got to be able to monitor its rotational attitude, its acceleration, and the altitude above the landing deck. And the rotational work of sensing is done with a 3-axis gyroscope, 3-axis accelerometer, and then the altitude with ultrasound sensors. Navigation sensors must detect current position on a map, compass heading, and airspeed and altitude. Now, one of the very cool things about many drones is that you can fly them using an onboard GPS navigation system. The Parrot AR drone, for example, has a pressure sensor for estimating altitude when the flight path gets higher than the ultrasound sensors can manage. And it's got that 3-axis magnetometer that we've seen before for compass headings. It also has 2 cameras, one pointing out front and one pointing down. And the one pointing down can be used to estimate the speed over the ground. Energy supply needs to be of high density because the cost of flying is so high. The primary cost is to stay aloft, to generate lift. If this can be done for free, as in a balloon or dirigible, the energy cost of flight is for forward propulsion only. Lighter-than-air craft suffer from needing a large size to carry gases. The large size makes them slow. So any rotary-winged aircraft, like a helicopter, quadcopter, or hexacopter, is in big trouble. The Parrot drone has a lithium polymer battery rated at 1,000 milliamp hours. It's pretty lightweight, and that's good. But the trade-off here is between weight and capacity. That battery only carries enough energy to power the drone for about 12 minutes of flight time. The heavier Walkera Tally H500 carries a larger battery for 25 minutes of flight time. Figuring out how long a battery lasts is actually quite complicated, because the rate at which the battery discharges depends on the load placed upon it by the motors, and motors are constantly varying their work. But we can make a rough estimate. Let's say that we operate the motors at their maximum combined power rating of 14.5 watts. Under that condition, we'd be getting a minimum time of operation. Now, this is a worst-case scenario, since most of the time the motors aren't operating at full capacity. Hovering, for example, should draw the least amount of current for a flight behavior because the drone is not trying to move forward as well. The highest rate of current draw should occur during accelerations, high-performance maneuvers, flips, and things like that create a lot of inertial force. Electric power is the product of voltage and current, and the current is measured in amps. So if we imagine powering these motors for an hour, that would require 14,500 milliamp hours of draw on the battery. Now we get 14,500 milliwatts by converting the 14.5 watts from using amps to milliamps. So now to fly the Parrot drone at max power for an hour would take a battery with 14,500 milliamp hours. Now the Parrot's actual lithium polymer battery only has 1,000 milliamp hours. So 1,000 divided by 14,500 is 0.069. We multiply that ratio by 60 minutes and we get about 4 minutes. Again, this is a rough estimate, and in real operation, the AR drone flies for about 12 minutes. You can also get replacement batteries that double that flight time, but there are always trade-offs, right? A battery with more capacity usually means a heavier battery. And a heavier drone means that the motors have to spin faster in order to keep that quadcopter hovering. Add a big enough battery to spin the motor for a couple of hours, and the drone couldn't even take off. So this is a clear example of the trade-off between the weight of the robot and the energy capacity of the battery. Control of aerial robots includes behavior-based systems that offer rapid reflexive corrections of flight systems using negative feedback control to do things like maintain proper flight attitude or engage in maneuvers. Rapid control is particularly important in inherently unstable aircraft like rotary wing vehicles or an air vehicle traveling at high speed. Also, certain environments produce wind turbulence, and that turbulence can be very challenging for micro drones in particular. Urban settings can be tough this way, since wind eddies form around the sharp edges of buildings. Most micro drones have operational limits on wind speed. For the Parrot AR Drone 2.0, that limit is about 9 miles per hour. Model-based control algorithms are needed for navigation to compute heading to the next waypoint, speed over ground, and altitude above ground. The challenges of controlling a robot in the air are exemplified by a simple behavior: object avoidance. Object avoidance is very easy to program in land-based robots like Roomba. Now, Roomba uses bumpers, IR proximity detectors, to do object avoidance. These are active sensors, the IR sensors anyway, that emit electromagnetic energy in the infrared range. The sensor also has a detector that is reading the intensity of the reflection of IR off an object. So one of the things that happens when we use IR is that it takes energy to do that kind of sensing. And imagine what would happen if Roomba were moving much faster than vacuum cleaners usually move. It wouldn't have time if it was going really quickly to both sense an object and then being able to avoid it. So that's why object avoidance with microdrones like the Parrot won't work with IR sensors, right? By the time you get close enough, you're too close to veer away if there's an object. So you have to be close to make them work, and then you would have to be slow enough, stop very quickly to be able to maneuver out of the way. So drones need long-range sensors. Large drones, like the MQ-9 Reaper, can carry radar, but micro drones can't. So two developments may soon help micro drones: the creation of small and lightweight radar, and the development of object detection algorithms that use video. Since many micro drones have video, this would be great. The problem is that to detect objects quickly with video, you'd need a fast computer. And fast computers tend to weigh more than slow ones. Now, given all these design challenges for drones, you might start to wonder, isn't anything easier in the air? Or is it all just challenges? Yes, there are some easier things. One of the fundamental challenges of robotics, navigation, is easier outside and in the air than, for example, being outside and underwater. And that's because GPS can be used outside, and at a height above the tree line or the highest buildings, very few obstacles exist. Aircraft-sized drones are large enough to carry sophisticated sensors and high-density energy supplies sufficient for long voyages. Drones such as the Global Hawk can stay aloft for nearly 24 hours. Since large drones operate primarily in unrestricted and high-altitude airspaces, object avoidance involves primarily other aircraft, and radar systems on board can be used in conjunction with land-based air traffic control. Speaking of air traffic control, we'd mentioned how a commercial aircraft flying on autopilot is operating as an autonomous robot. An autopilot is an example of an embedded or hidden robotic system, very much like your adaptive cruise control on your car. Autopilots are some of the earliest robotic systems invented, and they've been around for almost as long as fixed-wing aircraft. We've seen an autopilot at work in the Walkera Tally H500, and they work in a very similar way on commercial aircraft. Now, the most important thing that an autopilot does is to fly a plane in straight level flight. And this was the first function of the first autopilots nearly 100 years ago. Sensor-guided movements are the key to autonomous behavior in a robotic system like an autopilot. So we need a sensor that is linked to an actuator. And the sensor in the first autopilot was a gyroscope. So what is a gyroscope? Now, you may have played with one before. Let me pull it out here. Recognize this? Its official name is a Chandler gyroscope, after the Chandler company that made these toys. Let's see if I can get it going. I've got this piece of tape on here because I very carefully wrapped this up. And I'm going to give it a good spin here. And here we go. And put it, first of all, here. And so one of the great things about gyroscopes is that they're auto-stabilizing. Now I can try to tip it over, and I can put it on my finger, like so, and it balances itself. It doesn't like to move off its axis. And that's what makes these guys kind of magical. And actually, as I try to move it, it's resisting it. I can't share my feelings with you on this, but it's going, it's fighting me here. And what's great about this is that anytime I generate a tilting force, I can feel the gyroscope pushing back here. And this is related to Newton's laws of motion. So it's slowing down. Here we go. All right. So there's our gyroscope. The take-home is that forces of motion come in opposing pairs. You can't have one without the other. So how does the gyroscope do it? It's this balance of forces that Newton's laws predict. So the tricky, nifty thing about spinning tops or rotating gyroscopes is that their ability to generate a reaction force is proportional to how fast they are spinning. So they can balance gravity when they spin so they don't fall down. Now, while gyroscopic sensors started out as mechanical devices, like the one I just showed you, modern gyroscopic sensors are micro-electromechanical gyroscopes. These tiny electronic devices, the size of a human hair, contains a small mass that vibrates on tiny spring. As the device experiences the forces of angular rotation, that small mass changes its pattern of vibration. That change in vibration is then converted to a change in the electrical signal that the device is producing. The usual arrangement in a robot like the Parrot or the Tally is to have a 3-axis gyroscope so that changes in angular velocity can be detected in the 3 independent rotational axes: pitch, yaw, and roll. So you can see how you might put a motion-resistant, self-stabilizing, if you prefer, gyroscope to work for you in your robot. Well, Elmer Sperry certainly did, and he patented the idea in 1915. Now, Sperry didn't invent gyroscopes. What he did invent was a way to build motorized gyroscopes and put them to work to be able to accurately sense and respond to the movement of the world around them. So based on those gyroscopic responses, Sperry could then have the control system of the ship react, right? So there's this little force generated when I try to move this, so that's a way to measure acceleration. So a gyroscope is used to help stabilize a ship, and when it is, it's called a gyrostabilizer. So Sperry's patent and others that followed helped him build the Sperry Gyroscope Company. Now, even though Sperry started making automatic stabilizing systems for the Navy and for ships, he was interested in the newfangled technology of powered aircraft. So he filed a patent in 1917 to create an aerial torpedo. I find 2 things, and there are many more, amazing about this invention. First, the aerial torpedo is the world's first patent for an unmanned aerial system, as defined right now by the FAA and the Department of Defense. The second thing that I find amazing about Sperry's automatically controlled aerial torpedo is this. By including radio control and autonomous control, Sperry mapped out that entire control landscape that we've already discussed today. Now keep in mind that this patent was filed almost 100 years ago, in 1917. So the idea of drones and unmanned aerial systems being some modern invention is nonsense. Old school robotics, man, that's what it is. And in May of 1917, the Navy actually ordered 5 of the Curtiss N9 seaplanes to be modified into the aerial torpedo. On March 6, 1918, one of the aerial torpedoes, unmanned, took off and flew for almost a kilometer, becoming the first ever unmanned aircraft in a complete unmanned aerial system. What kept the unmanned aircraft operating autonomously was a system of gyroscopic stabilizers connected to actuator controls. A pitch up of the plane's nose is sensed and causes a signal to be sent via the controller to the elevators on the back of the plane to tilt the tail down. A negative feedback controller keeps adjusting the elevators to keep the plane flying level. Negative feedback control also works in the other axes of rotations, yaw and roll. So if a plane starts to roll, a gyroscope detects that motion and sends signals to tilt the ailerons on the wings. If the plane starts to yaw, the gyroscope detects that motion and sends signals to tilt the rudder on the vertical stabilizer. While the Navy lost interest in unmanned aircraft shortly after the end of World War I in 1918, Sperry went on to use the autopilot in manned aircraft. In 1933, Popular Mechanics published an article on the Sperry automatic pilot. The article said, quote, "On long runs, the robot pilot permits the human pilot to simply watch the dials while the plane is maintained on an even compass-directed flight at constant altitude. The automatic pilot functions twice as fast as the human pilot in making corrections, for tiny electrical fingers feel the most minute deviation from the course and corrects it before the human knows what is happening. While the development of the automatic pilot has reached a high stage of perfection, aeronautical experts reject the idea of using it to replace the co-pilot," end quote. But that was 1933. The autopilot on a modern commercial aircraft now flies in an environment modified with beacons from above and from below. We have GPS sensors that take advantage of GPS satellites. We have distance measuring equipment that sends paired pulses to transponders on the ground. In addition, Inertial guidance systems constantly calculate current position by dead reckoning, and there is typically a flight control system which can even sense and rebalance the fuel in the plane's tanks to even out the plane's distribution of weight. Not flying a lopsided plane, obviously, improves fuel efficiency. So commercial and military planes are now very sophisticated robots. This is what makes it increasingly possible not only to replace the co-pilot, but pilots, and not only in military planes such as Reapers, Predators, or Global Hawks. One of the long-standing challenges in flight systems, as we talked about earlier, is carrying sufficient energy to power your flight. Fixed-wing aircraft have an advantage over rotary-winged aircraft in that they generate lift by propelling themselves forward. Once you get airborne, you can take advantage of fixed wings by getting energy efficient as you go along, by gliding. So aerial robots can be built as gliders. Gliders move forward by sinking. The challenge is to catch an updraft if you can and gain height. The best gliders in the animal kingdom do just this, using the air rising off a warming mountain face to give them the height to glide over that mountain. Birds can also use a technique called dynamic soaring, and we see this in oceanic birds like albatross. The trick is to glide quickly through regions of increasing wind velocity. These wind gradients are found throughout the ocean with slow wind speeds near the surface and faster layers of wind as you go vertically. Dynamic soaring allows birds to travel for hundreds of miles without flapping at speeds of up to 30 miles per hour. Radio-controlled gliders have been able to go even faster, a lot faster. Radio-controlled gliders flying in a loop over mountainous terrain have been steadily breaking one another's records, with a new record of over 500 miles per hour reached using a kinetic 130 dp glider in 2014. With such results in mind, a researcher at Woods Hole Oceanographic Institution, Philip Richardson, has calculated that glider UAVs may be able to hit top speeds close to 10 times the speed of the winds they're riding, at least for small UAVs in slower winds. This is far more than any albatross could attain. Hybrids that use both fixed wing and rotary wings are also possible, and this approach has been demonstrated in the Makani Power Kite, which was the very first fully autonomous wind harvesting robot demonstrated in 2013. And it was bought, by the way, that same year by Google. Looking like a glider, this robot has a large fixed wing span of 26 meters, about the diameter of a high wind power turbine. But it also uses 4 turbines for takeoff and landing. Now the rotors capture wind energy, but when there is too little wind to gather energy, the computer powers up those same rotors to land the robot safely and wait for wind to resume. Similarly, Google X's Project Wing demonstrated a UAV delivery service concept using helicopter-style takeoff and hovering, combined with an airplane-style movement for better long-distance travel. And since there's no human pilot on board, the robot could flip from vertical to horizontal, something that would be disorienting if humans were on board. The result is a much simpler design than vertical takeoff and landing approaches the military has tried for piloted planes. Now, when discussing energy efficiency, we should also probably mention robotic balloons and dirigibles, whose main disadvantage is they carry so much gas that makes them slow. They have high drag. So high-pressure helium balloons were used by the Soviet Union's Vega 1 and Vega 2 missions to Venus in 1985. Each balloon was 3.5 meters in diameter and carried 7 kilograms of instruments in a gondola suspended on a tether 13 meters below the balloon. Floating about 54 kilometers above the planet's surface, an altitude where pressure and temperatures are more similar to the Earth's surface, each balloon operated on battery power for nearly 2 days. Now, robotic balloons have been tested high in Earth's atmosphere to approximate conditions on Mars. Now still, the biggest frontier is that the small flying robots that you've met, like the Walkera Tally 500 or the Parrot AR Drone 2.0, present a lot of challenges. Compared to larger drones, microdrones operate near the ground, in complex urban environments, and even inside buildings. Being so near the ground, a microdrone encounters a host of obstacles, including buildings, wires, and trees. GPS-based navigation systems suffer when proximity to a building puts the drone in a GPS shadow, unable to contact the optimal number of satellites for high accuracy localization. Micro-drones are worth all the fuss because we can put cameras on them. And cameras on board are exciting for a host of potential uses. We can do live and recorded coverage of parties, group gatherings, and outdoor trips, surveys for real estate firms, search and rescue, hazardous environment exploration, military surveillance, high-resolution weather and climate mapping, and traffic monitoring. So this is already an incredible array of work for aerial robots. And this list doesn't even mention all the other kinds of actuators drones might utilize, such as those you might use for agriculture, delivery services, firefighting, wildlife management, and so on. In many ways, what has happened over the last century in aerial robotics exemplifies the progression of robotics as a whole. First of all, we see partial autonomy and embedded robotic systems developed early on. Second, as small, powerful electronic computers develop and are paired with GPS navigation systems, aerial robots take off, literally and figuratively, extending their fully autonomous capabilities. Third, improvement in computer algorithms for dynamically unstable motion and for extending battery life make sure that we can build a larger range of sizes and different kinds of body types. So robotics has been key to improvements in aviation almost from the very beginning of flying planes. So the drones that seem to explode out of nowhere in the 21st century are really better seen as yet another step in the overall progress of aerial mobility. And someday, not soon, but someday, robotics may be how we finally get that flying car we've been waiting for.